This is just a brief introduction to doing 3D in monogame. So I've already kind of started a project here, but what you do is you go new project like this, and I'm doing a cross-platform desktop project, which is through OpenGL. If you wanted to, you could use any of these, change the name of the project, and then start it. And you should have this game one right from the get-go. The first thing we'll add is an input class. So you can right-click on the name of your project and add an input class. We'll just call it input, hit enter, and it'll be blank at first. You can get rid of unnecessary stuff for now. And I'll just pause the video, add some stuff here, and explain what I added. And if you want, you can pause the video and copy what I've added as I explain it. So the first thing we'll need to do is get some usings for some of the stuff that isn't recognized right now. So which namespaces are we using? And we're using this one. And we'll be using this one and the framework graphics. Here I'm using compiler services. So I'll start by explaining what these are. These are your mouse button states. I just have them as constants. So I got keyboard stuff here. This is your keyboard state that you capture each time it does an update. This is the old keyboard state. So the last time it did an update, it keeps track of what the state of the keyboard was. So you can compare the two to find out if a key has just been pressed or if it's being held down. There's a right shift and a left shift, same with control and alt. So I have these booleans to flag whether those were pressed, either of those were pressed or held down, and the old states too. It uses that to know if it was just pressed or not. And I do the same thing with the mouse states. It captures the state of the mouse, which buttons are pressed, position of the mouse, so on and so forth. And I've got for left click, right click, and the position. I got some optional things here for getting the position. But these three here are essentially the same. They're just the coordinates of the mouse in either a vector, pointer, or an int. And then I got the gamepad states, same idea. You got A button, B button, X, Y, right button, left button, your buttons and triggers, and so on and so forth. This one takes a little bit of explanation. What we do in the constructor of the input class is we accept the presentation parameters, which I'm going to show you in game one, where we get those presentation parameters and pass them in. And those represent information about the current state of your graphics card and your current state of your display, actually. And this render target is the desired resolution that you want your game to be made for. So the desktop resolution, which is your default resolution on your computer in windowed mode, is different than the render target resolution or main target, which is how you want your game to be represented. Like if you want it always to be 1024 by 768 or maybe a higher resolution, but your desktop resolutions may be higher than that. So in order for your mouse coordinates to be correct, because your mouse coordinates are always your desktop coordinates in windowed mode. So to get the correct coordinates for your target resolution, which is going to be like a virtual full screen, it's going to be sized like a full screen over top of your desktop. This helps us convert. We just multiply by this screen scale X factor and screen scale Y factor, and that'll get the coordinates in this target width, target height. And I'll show how these two parameters are used down below. We're just calculating them here for now, so we don't have to recalculate them every update. This optimization might not be necessary, but I just put this here to kind of force it to inline this if possible. So instead of calling the method, it's just going to try to place the code that would produce this sort of result wherever it can. For key press, it checks the last state of the key, which is old keyboard right here, and if it was up and keyboard is now down, therefore you know that that button was pressed. If it's down, then we just say that it's down. So it's just a sort of a wrapper to kind of simplify so you don't have to type out quite as much. And I do the same thing with the gamepad for button presses. Check the old state versus the new state, and then you know that the button was just pressed rather than being held down. So the first thing we do in update is we get the old states, the old keyboard state, the old mouse state, and the old gamepad state, and we just record them from what they were previously. And now we get the new state. Keyboard state is equal to keyboard state, get state, and we do the same with mouse and with gamepad. We got 0 here. If you go like this, you can see that there's an index for which player it is. So we're just going to go with 0 for the player 1 gamepad. Initially we set all the shift, control, alt to be false, and we check to see if either the right or the left are pressed down, and we set them to true if it is. If they weren't before and they are now, then we set the shift press, control press, and alt press to true. Here in the under mouse stuff, we get the vector, which we have to convert to float, the mouse's position, so mouse state dot position, and we do that for mouse state dot position y, and we're multiplying by these scale factors that we made up here, so that instead of the desktop screen position, it's giving us the main target position. Otherwise, the position won't be correct. It won't match. And then just for convenience, I also record these positions in integer and in a point. Point is handy because then you can just use a method to check to see if a point is inside a rectangle. And then same as we did above with the keys, we set all the states to false, and then we check to see if the mouse left button state is currently down. We set it to true. We do that for mid, right button, and then we compare it against the previous state, and we'll say left click rather than left down is true. So if we want to find out if it was just pressed, we can check the status of left click and mid click and right click. Gamepad stuff is again the same sort of thing. We're checking the status of button A, button B, button X, button Y, the right and left shoulder, which I'm doing as right button and left button press, and same with back button and the left stick, right stick buttons. And as far as analog goes, we'll get to that part later. So that should be it for the input class. If you want, you can pause and copy out segments of this code. Now if we go to game one, here I'll just pause a second. I started off by adding this display section, some constants for the game's targeted resolution format. So I picked 1024 by 768, which looks pretty good. This one's default. I added this graphics device GPU. You can just normally use graphics device, but I added this here just so I can say GPU dot instead of graphics device dot. So just for convenience. I'm going to be using a sprite font, so I added that in. And I'd like access to the screen width and screen height dimensions in a lot of different modules. So I made that static public so that I can say game1.screenW to find out what those are from anywhere in the project. I just added our input class here. I'm just going to use INP. It's 3 letters. You're not typing out quite as much. It's not as much to look at. It's easy to understand. And I added this render target here. This is going to be used like our back buffer. It will be at our desired resolution here for the game. And everything we render is going to be rendered onto the main target first, and then the main target's going to be stretched out to the desktop size so that that window covers the entire screen. So it's like a full screen. The reason why we're not actually using full screen is because I prefer to do it this way, because certain issues I've had with certain security software and stuff running in the background in the past where it could cause it to crash. So until the game is finished and everything is debugged, I would prefer to go with this rather than switching full screen resolutions. Here we got the desktop rectangle and screen rect, and screen rect is going to be the dimensions again of this target resolution. So just in case we need the rectangles for like doing a destination draw or something, we have these handy sort of things, so we're going to calculate those below. In the game one constructor, you usually have this graphics equals new graphics device manager, and we're going to need a desktop width, desktop height, and we're going windowed mode, so make sure you put before this content root directory, put window.isBorderless equals true, because we don't want the border on there. So here I was getting the desktop width using graphics adapter dot default adapter, current display mode dot width. I subtract, for debugging purposes, I'm subtracting 10 from width and height. Probably just height would be fine, just so I can click on the bar below and hit stop in the debug if something goes wrong. So that's just for convenience. Later on though, when everything's running smooth, you can take -10 out of these, and that should be the way it is. So we're going to set the preferred back buffer width to the desktop width and the desktop height. So this is the actual screen resolution settings. It's just going to match whatever your desktop is by default for windowed mode. Is full screen is false because we want windowed mode. And preferred depth stencil format, we don't have to set this to any depth, even though this is 3D, because we can do all the depth on the main target and then just render this as a 2D image onto the desktop when it's done. I'm using this graphics profile parameter equals graphics profile dot high def. There's also this reach, and reach is the default. Reach will only allow you to have 65K of indices, which normally is lots. We're probably going to use much more than that though. It depends on how much geometry there is in your models. So just in case we're going way beyond that, setting to high def is going to give us up to 4 megs of indices. So that's a lot better, and we're definitely not going to run out of indices that way. But what those indices are indices to vertices in the vertex list, which are going to be in what we call a vertex buffer, which in an optimal way carries vertex information over the graphics card. In Initialize, I started this display section, and just as a shortcut for convenience later, I set GPU to point to the graphics device here. So GPU basically represents this, and that just makes it a little shorter for typing and speeds things up a little bit. And I always know what GPU means. It's graphics processing unit. Presentation parameters, I'm just getting those for passing information along to other things. So I'm just get those locally here for now from GPU.presentationParameters, which again gives us information about our current display mode. And this is the typical setting up the sprite batch using the graphics device. Here we're creating a new render target, and we're using that constant screen width, screen height for the desired resolution that we set up above. We're just going to use the presentation parameters, the back buffer color format, and we're going to need a depth of 24. You could use depth 16, but you're going to have Z fighting issues, I pretty much guarantee it, and things aren't going to look right all the time. So that's why I would suggest depth 24 for your depth format. It will capture the screen width and screen height of the desired target resolution, so the game resolution. And for convenience later on, we'll also get the desktop rect, which is your default desktop display, and the screen rect, which is the desired game format. And we'll also have to make a new input object passing in the presentation parameters, which it needs to figure out how to do conversions, as well as the main target, and it's just getting the width and height of the main target used in that calculation, which you see right here. In the load section, we're going to want to load up the font, and I'm just calling it font. And what you can do, if you haven't already done this, is go into content over on the side, double click it, and go add new item. And in this case, we're creating a sprite font, and hit create, and you can name it right here, and we're just going to name it font. And then if you want, you can actually go into that file and change some of the parameters for the font, change it from Arial or whatever to something else. I'm just going to leave it as default, and then we can build. In the update, we don't really have anything yet. If we want, we could change this so that we use our input wrapper class instead. So I just quickly changed it to the input class version, and it's a lot shorter, easier to read, and this is just temporary because normally you'd want to exit with a menu. So we'll just leave it like that for now, for debugging purposes. Then there's our draw, and for now it doesn't really do anything. I'm just having it clear back buffer for the desktop, just clearing it to a transparent black. Oh yeah, I almost forgot. Go back up to update. This input stuff isn't going to work unless we actually call in.update. Now, if you remember, we said we were going to draw everything on main target, so go back down to draw, and actually we could actually go GPU.clear. First thing we'll do is go GPU.setRenderTarget, and we'll set to our desired game resolution. We'll set it onto that texture target. We'll render everything onto that, and then we'll render it to the back buffer, which is going to be the desktop display resolution. So actually, I'll just take this out for now. And when we're on the main target for rendering 3D, we'll want to set our 3D rendering states just to make sure that they're all set for 3D rendering. So we'll have to create a method to do that. If we're not rendering a background or not rendering a bunch of stuff to clear the buffer, what we could do is go graphics-device.clear. Actually, I'm using GPU.clear. And we'll use clear options target, and we'll also use clear options depth buffer. And we want to clear it to transparent black. And clear the depth to 1, which is as far away as possible, and stencil to 0. So then we would render scene objects. Oops. And here we're going to go GPU.setRenderTarget to null. Anytime you do that, it sets to the back buffer. And we'll just use sprite batch. And for blending state, we'll use opaque because we don't need any transparency. We're just stretching out the final image onto our desktop. Sampler state, we'll just go with linear wrap. Depth stencil state will be none. And rasterizer state, call none. should be good. Oh, this should have begin here. And then we'll go spritebatch.draw, and we'll draw our main target to the desktop using our desktop rect we made earlier. Color.white because we don't need to colorify it. That just means it'll color it normally. And spritebatch.end. And the end is actually where it actually renders everything. And this stuff just kind of prepares it. So we don't have this set 3D states yet. So probably after update, I just added this set 3D states here. And what it does is we set the blend state, because spritebatch is going to change some of our states on us, and we may change them along the way for other things too. So to get back to our default 3D rendering states, we'll set the blend state to blend state.non-premultiplied. GPU depth stencil state, we'll set it to default. And this actually may or may not be your desired setting for depending on what you're doing. But depth stencil state default, GPU, the rasterizer color mode by creating this state here, and then we'll just assign it to that. And that's only if it isn't already that. And if you run it at this point, you can see that you just get a black screen, which is what is expected, and you can escape to get out. So let's go back up to the top of our game1 class and add a test texture 2D. We'll use this for creating some basic 3D objects and use this to texture those objects. So let's just call it test texture. I just shuffle these around. I'm keeping the render targets and textures together. Let's go down to load and load that test texture. So in load content, we'll just say test text, and we're going to load a test image. So you can copy whatever PNG you like into your content folder, go to content, and you can add it from source and it'll copy it into content, or you can just have it in the file folder already, which is what I did. So I'm just going to add existing test image, add link, and build. Also go and make a new class for basic 3D objects. So I'm just going to call it basic 3D objects. So in here we could have things like floors or cubes or doors or just basic objects that are very simple, even a sphere. We'll start with creating something generic that we can expand from. So maybe we'll make a nested class here. Right, so I added this nested class. So each object has a start index. That's where in the index buffer the object begins at out of a list of indices. And then there's a number of triangles. So it could start at index 10 and then have, say, 4 triangles after that. So there would be indices ranging from 10 to 4 times 3 plus 10. And our texture map might have more than one texture source on it. So we might have a whole bunch of textures kind of placed onto one texture map, and then the UV coordinates would extract from that. So we use this source rect here to figure out where on that texture map we're going to extract our image from. And this is the texture itself. Chances are good we're just going to use the entire texture. So when we pass in null, if it reads it as null, it'll just assume that we're going to use the entire texture. You'll see what I mean in a bit. So this is for rotating, this is for setting the position, and this is the overall transform. We could add scale in here too, but we'll just leave it this for now. So the transform combines your scale, rotation, and position in this order: scale times rotation times position. The thing to remember is if you did translation first, then rotated it, it wouldn't be rotating in the center of the object. It would be rotating around where the object was originally centered around. So if you did the translation first and then multiplied by the rotation, you'd end up, if say the distance was 10 units from where it was originally was, the rotation center would be 10 units to the left of the object, and then it would rotate in a big circle rather than spin on a spot. So just something to keep in mind. I added these transform updates for assembling your matrices, which do the rotation and translation and repositioning of your 3D objects. So they don't have the scaling in them. Like I said, I'm not going to do that in this example, but we are going to do rotation and position. So I made 2 different versions. There's one that works with yaw, pitch, and roll. That's the y-axis rotation, x-axis rotation, and the z-axis rotation. We can use the matrix dot create translation to create a transform matrix that transforms, a translation matrix actually, that translates by position, and we just put it into this transform matrix that we're going to use here. And the transform combines all these So it combines the translation matrix, the rotation matrix, and so on and so forth. If there's no rotation, then it'll simply create a translation matrix in the transform for the position. If there is, then it's going to say the transform is going to be equal to the matrix for the yaw pitch roll, so the angles of rotation, XYZ rotations, and multiply that by the translation. So the translation comes after the rotation. The other version, which does the same thing essentially, uses quaternions. So it does the same thing, but it puts it in a quaternion instead of a matrix. And then you can go transform equals matrix dot create from quaternion, and then multiply that by the translation matrix that you create here. Supposedly, it prevents what they call gimbal lock. I haven't encountered that problem yet, so I more often have been using this one. That's for this nested object 3D class. But for our basic 3D objects, we're going to have some things that will need to be shared. So I'm just going to put right here obj 3D, so I know that that's the end of that. So I started adding some geometry variables that we're going to need. I got a matrix called world here, which will be for fixed geometry like landscape. You could shake it around and create an earthquake or do something like that if you wanted. And we're going to have a list of those sort of generic 3D objects, that nested class. So we can just add as many of those as we want of whatever type. We'll create different types as we go. We're going to need access to the content manager because I changed my mind. Instead of using this test texture here, I'm going to, well, we could leave that there for now. We're going to load the textures into each object. Actually, what we're going to do is we're going to have a dictionary that accesses each texture based on the file name. And if it already exists, then it won't load it. It'll just reference it. So you'll notice that these are all considered static. That's because I want to have access to them in my nested class. So that's why they're static private. And the index buffer is important. That's going to hold all the indices that are going to be transferred to the graphics card, and the vertex buffer holds all the vertices to be transferred to the graphics card and stored on the graphics card. And then that way, because they're in the graphics card's memory, they can be processed very, very quickly. The indices, I'm going to use a unsigned short list. So if we didn't use high def and we use reach instead, this would still work. If we needed way, way more indices, which is very unlikely in this case, then we could change this to like a UN32. We would never use that many for basic objects though, never. This is the vertex format I'd like to use, position normal texture. If you need more things like tangent for a more detailed render, you can create a custom vertex type, which I might show later. This is just the counts of the indices and the vertices that are being added. This is the starting location, the current starting location in the index buffer. So when we add a new object, it can use the last location in the index buffer to figure out where it should add as a start index the new object. I don't know if that came out right, but hopefully that makes sense. So I'll kind of show what's going on with this dictionary thing too. It's basically you're using the string itself like an index into the textures. It uses hash tables, so unordered maps. So it's quite a bit faster than you might think. Before we continue, I thought we'd create a look at matrix, which is a matrix that's used to sort of work like your camera. So we're going to create a camera class, and that way we can control the camera position and orientation fairly easily and pass it around as we need it. The way a look at matrix sort of works is you got your target, which I'm going to make as this tree here, for example, and then the camera position, maybe it's going to be this tree. And normally what you do is all your local objects, like all these little trees, if they were, say, moving in the wind or something, or if they were characters, they would move around, and they'd have what's called your local transformations, which is like local rotations and such. And then they have their world transformations, so that's where they move around in world space. The trees won't go anywhere, they'll just be in a specific world location. And the like characters or other dynamic objects would have their world positions updated. So once that's all done and everything, and you figured out where all the vertices are going to be in the world, what happens is when you run your shader for rendering your polygons, you multiply by your world transform matrix, a world view projection matrix, which is sort of your camera matrix or your look at matrix. And so say the camera's here, and this is what you want to look at. what it's going to do is act as though the camera is always looking down the z-axis and is at 0, 0, 0. So what it's actually going to do is take all the world coordinates of every object, of everything that's out there, and translate those by multiplying each coordinate in the vertex shader by that world transform matrix, or that world view projection matrix, I should say, which I'll show you later. So that look at matrix will be multiplied by all this stuff. And what it does is first it translates all the world coordinates to the right because the camera's to the left. So it's kind of doing the opposite. It's like the inverse. And then, so the camera's at this tree. So then we'll zoom in a bit here. And we want to look at that position over there. So say it's 45 degrees to the right. We got to rotate the world around the camera's position 45 degrees to the left, so the opposite direction, to get the correct direction that the camera's looking at. So that's essentially how it uses that matrix. Once it has it so that it's pointing in the correct direction, as though it's looking down the z-axis of the camera from the camera's position, because the camera has all the world vertices oriented relative to that camera position. So then everything's still orthographic. So we've got to make it use the projection matrix to give everything a 3D perspective. And what that does is objects further away will be scaled down. In what you're seeing here, everything's already using a projection matrix to get everything from 3D world positions to the equivalent 2D coordinates on the screen so that you get the correct perspective view. So what it does is stuff that's further away gets scaled closer towards the center of the screen, closer towards that 0, 0, 0, and stuff that's closer gets scaled bigger. So it's all relative to how far in the z distance it is relative to the camera. So how much depth it has from the camera into the object. So if this was not using projection matrix, these trees would be a lot larger and would probably be over here instead of over here. So that's a rough idea of how that works. Not that you really need to understand that perfectly to use it, but I just thought I'd throw that in there. So let's start by building our camera class. So go over to your Solution Explorer, right click on your game's name, and add a class called camera. And I'll just remove unnecessary for now. I started adding some variables to the camera class, and some of these you might not need or use, like camera height offset, for example. This will depend on the size of your character. I got it set to 80 units up, so it's instead of the camera looking at the character's feet, the camera is going to look at the player's head instead. The far plane, which I'll show you how we're using down below when we create the viewing matrix, the far plane is used for clipping things that are too far away for the camera to see, and the near plane kind of clips things that are behind the camera. So if the camera is at 1, anything between 0 and 1 is not going to be seen. So that's part of the frustum clipping. And when we make our field of view, that also helps set up the frustum, which is sort of the viewing cone, although it's not really a cone, it's more of like 6 rectangles for clipping polygons out of the scene. So a lot of that's taken care of by the hardware. The camera position is here. The target that we want to look at is here. So if we change the target and the camera position, then we can do an update on the matrix based on that. This is the viewing matrix, which like I said, this transforms the vertices of the world to camera relative coordinates for projecting to the screen. And then the projection matrix does the actual projection, perspective projection to the screen. The up vector you can use to change which direction is up. I'm actually using down as up because I forget whether that's -1 or +1, but some of your programs may have -1 is up or +1 is up. So you can use that to flip the Y direction, and this will kind of get passed around between various classes. So anything that accepts a reference to the camera can look at this up vector to determine which direction's up. It's also used in building our matrix for looking at the world correctly. Current angle is, as I put here, the player relative angle offset of the camera, and we'll get more into that later. That's if you want to rotate the camera around the player using one of the analog sticks. This is the speed of the rotation of the camera around the player, and this is the radius, the distance of the camera from the player. which can also adapt based on how fast the camera, or how fast the character is moving and how close the camera should be to the player based on the scene. Unit direction is the normalized direction of the camera. So I'll show you what we're using that for later. The most important things though, and you'll probably need it in any camera class, is this position target. Far plane, near plane, you could hard code that if you wanted. And the viewing matrix and projection matrix, the up direction you'll need. View projection is just a combination of these two matrices. So if we don't have to update these, it's just a shortcut so that we don't have to keep calculating this over and over again, multiplying this by this if they don't change. And we'll need access to input if we want to be able to control the camera from within the camera class. Okay, I started adding this constructor for it, and we pass in the graphics device or GPU. We could pass in the up direction, or optionally just hard code it in here. I'm going to pass it in and pass in access a reference to the input right here. So capture the up direction. We set an initial position. I just have it hard coded so that the initial position of the camera is 20 to the right, 30 up, and 50 backwards from 0, so in the negative direction on the z-axis. The target initially is just looking at the origin of the world, which is 0, 0, 0, and we create the viewing matrix. So we got this matrix.createLookAt, takes the position, what we want to look at, and the up direction to create the viewing matrix, which will transform all the world vertex positions relative to the camera correctly. And then the projection matrix, create a perspective field of view matrix. The field of view I'm setting is pi over 4. So you got these other ones, and this would be 45 degrees because pi over 2 is 90 degrees and pi is 180 degrees, or 3.14, which you'd never use for that. And then aspect ratio, that's going to be based on your screen settings. So I'm just using the viewport aspect ratio, and what that does is it's like multipliers or scalars for correcting the final projections of the vertices relative to the resolution of the screen. So like if the screen is wider than it is taller, it'll adjust those positions appropriately so that they're not stretched in one direction or the other inappropriately. For the near plane, as you can see here, near plane distance, I'm setting to 0.1. A lot of people put it at 1.0. I don't think you can put 0. I think it has to be something like 0. You could even probably go 0.01, but I don't think you can use 0. And then I just got the far plane here, which I have as a constant up here, so I can just go into here and change it when I want to. And I'm using 2000. And this will be dependent on what kind of units you're using in your world and that. I combine this just so I don't have to recalculate it multiple times. And then the initial unit direction, I just get the viewing matrix forward direction, and then I normalize it. So what that is, the view matrix dot forward vector is the direction that the camera will be looking at any point in time. We'd have to update that if the camera viewing direction changes. This normalized vector, unit direction, is that vector with a magnitude of 1. That way you can point a vector in any direction you want, multiply it by the desired magnitude, so how big you want it to be, and you'll end up with a vector pointing in the correct direction that's exactly the size you want. So if you want it to be 15, you just times it by 15. And that way we can use the unit direction vector of the camera's looking direction, and we can multiply it by a radius or distance to the player from the camera, and kind of position the camera so that it's that distance away from the player in the opposite direction. You'd have the backwards vector from the player to get the camera to where you want it to be. Well, we'll go more into that later. Okay, so I just added a couple of simple methods for moving and orienting your camera. The move camera takes move vector, which is how much you want to move the camera by in whatever direction. So all you do is add the vector of motion that you would like to add, update the viewing matrix using the new position, and make sure you update your view projection because the view matrix has changed. To update the target, which is typically going to be the player position if you're looking at the player, just keep track of the target in case that's needed for other things. And I temporarily have this so that the target is adjusted to be -10 up. We could use this to, not using it at the moment because we're just going to go 10 up from whatever we're looking at for now. And again, we just calculate the viewing matrix, except with a different target, and then update the view projection matrix because the view matrix has changed again. Okay, I added this simple update player cam, which currently doesn't really do any kind of player camera update other than to temporarily allow you to adjust the camera position. So instead of using move camera, I'm just having, when you press the keys, it changes the camera position here. So we don't want to call move camera because we've already modified the camera position. So instead we call update target, and we're not changing the actual target position. We're just going to look at the origin, which is the center of the world. But we can change the camera's position. It'll always just look towards the center of the world though. But later on we'll adjust this. If you wanted, you could add additional controls in here temporarily for changing where it's actually looking as well as where it's positioned. But we'll use this for now. Later on we'll change it to this hero position once we've created a hero that we can move around and we can have it look toward the hero. But for now we're just working with basic 3D objects. Now that we have our camera class, let's go into game 1 under the display variables and add a camera. Just call it cam. Then we'll go under render targets, textures, create some space here, and we'll add our basic 3D objects, basic 3D, which can be floor or cube. Those are the two objects we're going to add. So we need to go back to basic 3D objects and make sure we set it up so that we can create these types of objects. So let's go to that class. So in basic 3D objects, I added this section here above this title geo where we had these variables from before, and we're going to pass in access to the graphics device, so we'll need that. I'm going to use this basic effect temporarily. Later we're going to use our own light effect, and we'll want to know what the up direction is so that we know how to construct our objects correctly. For getting the position in the index buffer and vertex buffer in bytes, we need to know how many bytes a vertex is. So the number of bytes for a vertex, in our case, it's going to be 8 floating points, 3 for position, plus 3 for normal, plus 2 for the texture coordinate, which adds up to 8. So we say 8 times the size of a float, and that's the number of bytes we need. And for index bytes, we'll just use the size of a U-short, which is 2 bytes, because it's 16 bits. So I'll show you how these are used later on. Alright, so we just added this basic 3D objects constructor, which is going to accept the GPUs so that we have access to that object, and we need to know what the up direction is, so whether y is -1 or +1, and we're going to need access to the content manager so that we can load textures. Later on we may also pass in whatever kind of light class that we'll use for setting up light effects. For now we're going to set the world matrix for the world geometry to be the identity matrix, which just initializes it. It's like setting it to 0. Basic effect is equal to a new basic effect, passing in the GPU, and we can use that for doing all kinds of shader effects, which is built into monogame. And we're going to need a bunch of vertices, which are going to be of type vertex, position, normal, texture. So position, normal, and texture are going to be the 3 things that we need to use in our shader for this. We can create custom versions too, which I may show later. We can use up to 65,535 indices. Technically we have high def set, so we could actually use more, but we're just going to use 64K of indices for this, because that's the most we should probably ever need for basic objects. So this is just setting up the new dictionary, and we're going to call it textures. So it's basically an array or a list of textures that uses strings, which is the file names, as an index into which texture it is. So we can look up our textures that way. So in DirectX or OpenGL, you're always going to need to create a vertex buffer and an index buffer, which are specialized for sort of optimizing and locking memory for use and sending to the graphics card. So these vertices go into the vertex buffer, these indices are going to go into the index buffer. And it's going to need to know the type right here, so whatever the desired vertex declaration. And here it'll need to know how many vertices we want. Buffer usage, we're just going to go write only. Index buffer, same sort of thing, we're using U-short. We could otherwise use like an unsigned integer 32 for high def, and this is the maximum number of indices that we're going to use. And here we're just setting up memory for a list of object 3Ds, which is that nested class that we're still working on up above. So we can put various types of object 3D into the basic 3D objects class. So the next 2 methods I just added are addVertex and AddTriangle, which we're making static so that we can provide access to these object 3Ds so that they can add vertices and triangles triangles to those objects. So these are going to be common functions to both of those, or common methods, I should say. So we can take the XYZ position, a normal, and a UV coordinate. When we first start adding vertices, the vertex buffer start position is going to be 0, vertex count is obviously going to be 0, and we'll just keep adding vertices and incrementing v count, which is the vertex count, until we're done creating the object. If we create a new object, vertex buffer start is going to be whatever vertex count ended off at. That way we can append or add the vertices for the new object onto the end of where it left off. So that's why we add these two together, to see if the total vertex count is greater than the maximum amount we're allowed. If it is, we can put out this console warning. So we create a new vertex at vertex count when we're adding a vertex, and this is our vertex type we're creating. We pass in the vertex position, pass in the desired normal, and we pass in the UV coordinate to create that vertex. Then we just increment how many we increment our vertex count, and we just keep adding vertices until we've created all the necessary vertices for that object. What AddTriangle does is it takes indices to vertices, and each index essentially tells it which vertex it's supposed to use. So if the first index is A is, say, 7, then we'll use vertex number 7, which has all this vertex coordinate data in it. And so you got 3 vertices, and thus you got 3 indices to make up a triangle. So if you want to build an object, you can reuse vertices using indices pointing to the same vertex. So some of the triangles will share indices depending on what kind of object you're building. We check to see if our index buffer plus 3 indices is going to be greater than the maximum amount that we want to allow, and we put out a warning if there are too many. So a plus equal to the vertex buffer start. So if we've added a bunch of objects or a bunch of triangles and we're starting a new object, the vertex buffer starting location is going to be different. So the indexes aren't going to be like 0 to 100. They'll be like 100 to 200, for example. So we got to add on where the vertices start in the vertex buffer. Just so I don't have to put a U-short vertex buffer start in front of all of these, I just say offset is equal to this, and then I add it on to all of these. That way the indices are pointing to the correct vertices. And so I record each index, and as I do that, I increment the index count. So I do that for A, B, and C. Oh yeah, I got this note here. Must cast again due to math always converts to int32. So yeah, that's the other reason why I did it like this, because if you just say is equal to A, which is a uint short, plus u short of vbuff start, for some reason when it adds the two together, it's still going to give you an int32, which is going to cause problems. So I do it this way to make sure that it's going to be a u short for sure. We'll also want our objects to be able to load textures based on a file name, which we can pass in here. So it's a static texture 2D, which is returned and kept track of in the object. Load texture based on the name. So first we create a texture, and what we do is we access the dictionary that we created, which, yeah, we created the dictionary here, textures, which uses a string essentially as an index. So we try to get the value of whatever was passed in to see if it already exists. If it does, we simply return a reference to the texture that was found. We got this out texture here, so whatever texture was found will occur right here. So if it did find it, texture goes out from here and we can return it here. If it didn't find it, then we can use the content manager to load the texture based on the file name, and then we can add to our dictionary that current texture and the name that's associated with it, which will be used like an index, and then we return that texture. So go back up to the top of class basic 3D objects and go to the nested class for object 3D, and we're gonna create a basic init method that each of the 3D objects can use. Alright, I added this init here, so you can initialize an object at a position and you can give it the file name for whatever texture it's going to use. We'll say that the start index is equal to the current index buffer starting position. So if some objects have already been created, the start index will start at wherever the index buffer start left off. You just get the position, and we set a transform matrix for this object based on the position. Then we load the texture using the file name passed in. If the source rect width or the source rect height are less than 1, basically it's an empty rectangle, then
we're just going to assume that we're going to use the entire texture. So the source rectangle will be the start at the top left, 0, 0 to the bottom right, texture width, texture height. Alright, so I added this get UV coordinates, and I'm making init and get UV coordinates protected, so it's like they're private, so that I can return the UV for the top left and bottom right. I'm using references here, so we're referring to the address of the U and V variables here. To get the UV coordinates, I take the sourcerex .x, which is the top left-hand corner, and divide it by the texture's width, and that'll get the coordinate in 0 to 1 space, because all your texture coordinates are between 0 and 1, whereas 1 is 100%, 0 is 0%, obviously. And so I do the same thing for the y, divided by the height. Then to get the bottom right-hand corner, I have to take the top left corner of the source rect plus the width to get the bottom right-hand corner position on the texture map. Then I have to divide by the texture width to get it so that it's in 0 to 1 again. Same sort of thing for the v2. All right, so I created this public add quad method, which takes a position and width and height, where the position is the center of the quad, and this is the dimensions of the quad, some initial rotation, the string for the file name of the texture, and the option of a source rectangle to extract an image off of the texture. So if there's a whole bunch of different little images on the texture, this is the portion that we want to use for our UV coordinates, and that's where on the texture to map from. So if the source rectangle had value, if it wasn't passed in as null, then we can say source rect is equal to whatever that value is, and that's source rect underscore, so that's this source rect here. So then we call init position and the texture file, which goes up to here and records the position of the object and sets a transform matrix based on that position, and then loads the texture. If it already exists, then it just gets the reference to the texture that's already loaded. So we also set the rotation here, and then we have to call the update transform, which updates the transformation matrix taking into account the rotation, because rotation is not 0. It's going to do this part right here because this is false. So from the yaw, pitch, and roll, creates a rotation, then multiplies it by the position translation matrix. And then that'll get the object's coordinates and record them in the transform matrix. So where we want this quad to start off in the world. Get the half width and half height as being the width and height of the quad divided by 2. Initially the UV coordinates are set to 0 to 1, but then we use get UV coordinates to get the actual UV coordinates. If we have a source rect, that might return a different result. I mean, technically, if source rect is null, we could even set this to 0 and 1 and just skip this step. So we initially set a normal, which is a surface normal, which is a little arrow that points directly away from the plane or the polygon. So we can use the normal to determine lighting calculations and whether or not the polygon's facing towards the camera. And then if it's not facing towards the camera, depending on whether it's clockwise or counterclockwise culled, it'll remove that polygon completely and won't calculate for it or show it. But that's what the graphics card is going to take care of that part. So we're mostly concerned about using normals for calculating lighting. So each vertex has to have a normal associated with it, which is the direction. It's the direction that the polygon's facing. However, at the corners, you might have an average direction based on other polygons around it. So you kind of get an average shading across the surface so that it won't look so flat. It'll look a little smoother, but that's getting into a little more advanced information, so we might get to that later. So initially I just set the polygons so that it's facing up. So I say y is equal to almost like a floor tile. So the y position is equal to the position y that was passed in. The left is equal to negative half the width plus position x. Doesn't matter what order you do this in. And then right is equal to half the width plus the position, and the position is the center. And then the near, or n, coordinate is going to be negative half the length plus position z, so closer to the camera. Far is going to be the half of the length plus the position z, again, which is the center z position. So then we can add vertices to create the quad from that. So we go left, the y position, far position, so your x coordinate, y coordinate, z coordinate. So that's the far left position, and it's all going to be on y, on the y plane, at 0 essentially. So left, far, and then we use the normal, or we pass in the normal, which is going to be straight up, and then the UV coordinate of the upper left hand point, then the right and far coordinate, which is going to be the upper right hand point on the texture, because we're going in a clockwise order here. Then we use the right and near coordinate, so it'll be a bit closer to the camera on the right side, and we're going to use the bottom right texture coordinate, and then left near, so we've gone completely around in a circle clockwise, so we're on the bottom left hand texture coordinate here. And then we can add the triangles based on the indices that we need, so 0, which is the first one, 1 and 2, and that'll make a triangle going top left to top right to bottom right if you're looking at it from above. And then 2, 3, 0 would be the bottom right, bottom left, and top left, again, if you're looking at it from above. So now that we've added these triangles, we can add those to the index buffer, and we can add to the vertex buffer what we created here with these add vertex. So what we do is we say vertex-buffer.setData, and then we have to declare here what our vertex declaration is, which is vertex position normal texture. So the type, the vertex type. And what we do is we take the vertex buffer starting index, where in the vertex buffer we left off at, basically, on our last object. Since this is the first time we're making an object, this would be 0. But if it was our second object, it might be like 100, for example. Multiply that by the number of bytes there are for each vertex to get the offset. So if you look here, offset in bytes, that's where we want to start adding vertices. And then these are the vertices, the vertex array that we want to add. And then this is the start index within those vertices that we want to add. So we want to add all of them. So we're starting at 0, and we're going up to v count, which is the vertex count, which is the number of vertices that we added into verts. And after we do that, we set v count to 0 because we've finished with this object. So we'd start again building up vertices and a vertex count for the next object that we create. Again, here, the vertex stride is just the number of bytes that are in a vertex. And so we update the vertex buffer start by remembering where we left off, and we left off at v count. So we can use that next time right here to get the offset in bytes. For the index buffer, we're going to be using ushort. And same sort of idea, the index buffer start times the number of bytes in, since this is ushort, it should be 2 bytes. If we're using a uint32, it'd probably be 4. And then we pass in our list of indices, or array of indices, starting at 0, using all of them, and keep track of where we left off when we were finished, so that we can use it next time when we create our next object to get the offset, and reset the index count to 0 so we can create a new object starting at 0 up to the new I count. That's the hard way to add quads, basically. The easy way is, for a lot of this stuff, is just to load models. So we'll get into that later. Easy in some ways, hard in other ways, but you can do a lot more complicated geometry a lot more easily. Okay, so I added a method for the second obj3d object type, public void add cube. Same thing, position, which is the center of the object, the size, so the x width, the y height, and the z depth sort of thing. So that's why it's a vector 3. The rotation, so we can rotate around x, y, or z. Oh yes, I should mention the rotation position stuff is actually factored into the transform. So if you didn't want a flat floor here, for example, and you wanted it like a wall, then you just use a rotation for the x-axis to rotate it so that it's a wall that you're looking at, for example. So it would be a 90-degree rotation on the x-axis. Alright, so for add cube, it's the same sort of idea. We store a rotation and transform here for the position and rotation. We add a texture file if it hasn't already been added. We get the UV coordinates off of the, if there's a source rect, or we just use the whole texture. And so we set a top, bottom, left, right, near, far, based on half length, half width, half height. And then we set the normal to be up, and then we add the vertex, the vertices, to create one of the quads. Like, for example, this is right, top, near, and then u2, v2 would be the bottom right coordinate on the texture map. So for these sort of simple objects, you can see why setting these up manually is kind of a pain, and where it's a lot easier to use a 3D program and then just load objects. I'm just showing how this can be done manually for this tutorial and for comprehensive purposes. So here we're adding all the indices. Same thing. we're appending vertices of the new object based on where we're starting in the vertex buffer and multiplied by the number of bytes in a vertex to get the vertex byte offset, and reset the count again and keep track of where we were, and same sort of thing for the indices.
When I get around to doing future tutorials, I'll show you how to use the model class that's built in the monogame and ways of kind of customizing your own model classes and stuff, which will allow you to import meshes, and it'll be a lot easier for you to create your 3D objects that way. So for now, I'll just stick to the basics here and how you could actually manually sort of set this stuff up. So we're going to use a basic effect for the lighting, and eventually we're going to add a light effect of our custom light effect. So if you go back to the constructor for your basic 3D objects, I added this init section here, and this is for the basic effect that we put in here for controlling how our polygons are rendered. And there's a lot of different shader effects built into that, but we're just going to use the default ones for this vertex type. So this basic.alpha is how see-through the polygons are. I think this is by default 1, so you may not necessarily need to set this here. And I'm going to make sure lighting is enabled, so I set that to true. I like to set an ambient light color, so that's for parts that are not lit, that would be black or in complete darkness. You can give them a little bit of ambient light so that they're at least visible. I would like to do a little less red and a little more blue, so like 0.1, 0.2 for the green and 0.3 for the blue, because in the shadow it's usually kind of a bluish tint, and if you look at lighting in like winter settings and stuff, you'll notice there's sort of a bluish tint. So that's kind of why I did it that way. If you wanted it more purple, you could go like 0.3 here, 0.2 here, and then maybe take the green down to like 0.05 or something. For diffuse color, so that's basically the brightness of any lit pixels or texels of your texture. So it's like a multiplier for how bright each one of those is. I got them at 94% for RG and B, so just a standard kind of white multiplier. And I make sure enable default lighting has been called, and I set to texture enabled. I got a comment here that I added vertex types, or the vertex type needs normals for this to work. So if you are just using like a texture type that is like, say, position color texture or something, it doesn't have a normal, then the lighting won't show up. You won't notice it. So just make sure that you're using something that has the normal on it. And you can create custom vertex types too, which we might get into later, where we could say vertex position, normal texture, and color, whereas texture here is for the texture coordinate. That's the UV coordinate. Alright, anyway. Now if you go down under load texture, you can add these two methods, which I added, which are basically just calling the add quad here and the add cube here through the basic 3D object class, because this is a nested class and we don't have direct access to this add quad, add cube. And in here, if you wanted, you could add other properties to your floor sections or cube sections or whatever it is that you're using, like if it's a door or if it's a breakable block or something like that. All I'm doing here is creating an instance of an object and then adding a quad to it and then adding that object to the list. And then here I'm doing the same thing, except I'm adding a cube based on the parameters passed in. And I would say just keep in mind that this mid position of your floor or your cube or whatever, that is where it's going to rotate around. So you probably want to just use vector 3.0, which is 0, 0, 0, and it's going to build around that coordinate. It's going to build that object. For controlling the actual position, you'd set the position of the object, which I'll show you later, and call the update transform method. So you'd actually set this position and then call this, and that's how you'd actually change the position. Or if you wanted to change the rotation and the position, you could do both and then just call update transform. So specifying an initial mid position that's offset from 0 would modify your center of rotation. If it's a floor piece, you're probably not going to rotate it, so it wouldn't matter, so you could just position them anywhere you wanted. If it's a cube and you wanted it to rotate, though, for example, then you'd want to position it around 0 and then for creating it, and then use the transform to actually place it in a position. Okay, so I added this draw method now, and we're passing in the camera, and we'll have to make sure we got all that set up in game 1. So the first thing you have to do is set the vertex buffer and set the index buffer. Now, for some reason, we don't have a GPU.set index buffer. but instead we have a GPU or a graphics device, because I'm using GPU for short. That's your graphics device. Graphics device dot indices equal to. Not sure why it's like that, why it's different, but that could be a bit confusing. But you need to set your vertex buffer and then set your index buffer this way. So we're going to go through an object count and loop through the objects. We're only going to make 2 of them, and we'll refer to the objects this way. We'll just say ob is equal to that object, and then we can just say ob dot instead of having to say objects o dot. So for the basic effect, we need to set the texture. We need to set the world transformation matrix, which is going to be ob.transform, and that'll control its position and orientation in the world. And we also need to pass in information about the camera, so the viewing matrix and the projection matrix. So the shader will use those and adjust all the coordinates so that they're matching our camera view, our desired camera view. So if there are different passes, it would have to go through a loop. So the standard way to do this is just to say for each effect pass in BasicEffect.currentTechnique.passes, and it goes through each one, and then you apply that effect. If you know your effect only has one pass, you can just use the currentTechnique.apply. And then we use this GPU or graphics device.draw indexed primitives. And there's a bunch of different overloads for this, and there's also a draw user index primitives. In this case, we're just using this basic one here and saying primitive type dot triangle list. The base vertex is going to be 0. The start index of the indices of triangles to draw is going to be whatever the start index is for that object, and then the triangle count for that object. So object 2 would start at, I think, index 4, because I think there's however many. Yeah, because we did indices 0 to 3 here. So it starts at index 4. So that's all there is to the basic 3D objects class that we were making for now. Let's go to game 1 and make sure we got everything we need in place so that we can use this. So we added this before. We'll need to go into the initialize and create an instance of this basic 3D. Okay, in initialize, I added this spot here, this init 3D stuff. The camera, pass in the graphics device. For the up direction, I'm using vector3.down. So up is going to be negative to kind of match with the way the models I'm importing are going to be. And we pass in the input class so that the camera has access to it if you want something in the camera class to be able to be controlled by that input. So basic 3D just takes GPU, whatever the camera.up is, which was passed in here. So now camera.up is actually equal to vector3.down, and pass in the content manager so that we can load textures directly inside basic 3D. And we made this test texture here before with test image. And I added this here now in load content, and I am instructing it to load test image for this one. It's going to try to load test image for this, but it's going to see in the dictionary that it's already loaded, so it's just going to refer to it. Since we don't need this test text here, I'm just going to take that out, and we can go up here and take out this test text here, because now that's going to be taken care of inside basic 3D objects. So this is going to be objects, this will be object 0 because it's the first one, this will be objects 1. So we call add floor, the dimensions are 200 by 200, the middle of it's just going to be 0, 0, 0, the rotation, the initial rotation of it's 0, 0, 0, but if you wanted it to be a wall or something, you could say like, you know, pi divided by 4, comma 0, comma 0 to rotate it on the x-axis. And then the image we want applied to it. For the cube, I give it dimensions 50, 50, 50. So width, height, and length are all going to be the same. Same sort of thing, and we definitely want that to have a middle of 0. For the rotation, initial rotation, we just leave it 0. For the texture, if you wanted to use a different texture and you wanted to use source rectangles, you could also set it up so that each face has its own image on a texture. Then you'd have to change the UV coordinates for your cube so that it's actually going to extract for each face from a different portion of that texture. And then anytime you want to make a new cube that has different images on the faces, you'd just kind of use that template and copy it. So you'd do that with each image that you're going to use for your cubes. And like I said, this initial position here is actually for the middle position where it's going to build the cube around, which we want at 0 because we want it to rotate around 0. So to actually position the cube initially, which is object 1 instead of object 0, we just set the position here like this. So it's 30 to the right, 40 up because our up vector is vector3.down, so it's negative. So up is actually negative 40. Negative 30 is towards the initial camera position, so negative 30 in the z direction. Okay, so I added to the update method some stuff for being able to move the camera around. To move the camera around, I just added this really simple call here to .move camera, and I'm using the thumbstick, the analog basically, for the gamepad. So this gamepad .thumbsticks, and then you got these different options here. So I'm using thumbsticks, and .left means the left analog, and this is the X value of the left analog, and so we're passing that in to control that rotation, and then same, and we can use the right one analog and its Y to control the Y component, and then I use the Y value from the left stick to control the Z. So that way we can kind of control where the camera is kind of looking, controlling the camera position essentially with the analog sticks. To move the cube around, I just did this simple thing with the arrow keys and the A and Z to go up and down, and if any of those are pushed, then it just adjusts the position. It's calling the update transform every frame for that because it's going to change all the time anyway, because I got this rotation constantly happening. So I'm just adding to the rotation around the y-axis just for fun. So in the draw method, all we have to do is add this basic 3D.draw and pass in the camera so that it has the current camera's viewing and projection matrix available to BasicEffect so it can draw it correctly. Now if we compile this and run it, it should work fine. So I'm using the left analog stick to kind of position the camera, and I can use the right one to go up and down. And yeah, so now we got a couple of basic 3D objects. In upcoming tutorials that I'm hoping to find time to do, plan to do some models and model manipulation, and we'll get into some slightly more complicated things. Thank you for watching.